So hello everyone, thanks Chris for the welcome. I'm Rebecca King. No, I'll step up a moment. I'm an assistant engineer working at Amy Consulting in Sheffield. I'm here today to talk to you about my paper which outlines the assessment methodology that we've adopted for a number of half-joint assessment schemes for bridges in Cumbria. Just to outline what's going to be in my presentation, I'll do a brief introduction about myself. I'll then talk about what actually is a half joint, which might benefit some of you, and why is there a need to assess these half joint elements. I'll then go through the basic concepts of our assessment methodology and talk about some of the issues we came across along the way and how we overcame these. So a bit about myself. I'm a graduate of the University of Sheffield. I graduated in 2016. I joined Amy Consulting as a trainee engineer. I did summer placements in 2014 and 15, and then I joined as a graduate full-time in 2016. So throughout my time I've done a number of structural maintenance schemes, structural assessments. In November last year is when I started work on the half-joint assessments, so that's what I'm here to talk to you about today. So firstly, if I could have a show of hands, how many of you are familiar with what a half-joint is? That's about what I was expecting. So I'll just outline, so a very basic bridge span here. I can highlight the bridge joint locations, and this is what a half joint arrangement looks like. So bridge joints, they're there to allow for movement of the bridge deck through thermal expansion and contraction, things like that. A half joint is comprised of this upper section here, which is supported by a bearing, which is then supported by the overlapping lower half joint section. So there's a number of benefits to using half joints. Firstly is that it really simplifies the design process. So if you look at the section between the two red circles between the two half joints, it can be designed as a simply supported span, so it's very quick to analyse, very simple. Also for construction, it also simplifies the process. You come in and you build your two cantilevers, one on either side, and then you can prefabricate your beams off-site, bring them onto site and drop them into place. It's really quick and simple. Unfortunately, there's also some drawbacks to using half joints. When you've got the surfacing running across the top, when you get the deterioration of that surfacing, you get very chloride-rich water coming down into the joint and sitting on the horizontal bearing shelf surface here. So this chloride water, it's got all of your sort of gritting salt that goes on the road, it's all that dissolved into it, and it's extremely corrosive substance. So when it gets into the joint here, it really accelerates the deterioration. It leads to corrosion of the reinforcement, and then the concrete starts to spool off. So that's what you can see in this photo, just the sort of horizontal lines you can see underneath the slab. That's where the reinforcement's corroded and spooled off the concrete. You can also see from the photo that in half joints you can't really see much of the joint at all. So this is another big problem for us. You can't get inside the joint. It's very inaccessible both for inspection and for maintenance. This obviously leaves us with quite a big problem. Unfortunately for us, half joints were extremely popular in construction between about the years of 1960 to 1980. As you can see, there's an awful lot of these half joint structures out on the network. I've just broken down some of the numbers, so you can see they're placed on some real sort of strategic big motorways, and this is the number that's just on the motorway and trunk road network, so there'll be plenty more on sort of local authority roads. So obviously this is a big problem for us. We've got a large number of these structures spread out across the country. In some cases they carry the motorway, so they're real big structures, and these structures have elements in them which are both prone to deterioration, and it's very difficult to go and inspect and detect that deterioration. So we have a real high risk here of sort of real explosive collapse, and that does happen. This is a half joint structure, it's in Italy. And there was a high sort of a lorry going across the bridge, and the bridge did fail due to the half joints. There's actually CCTV footage of the failure. It's quite alarming and a bit disturbing, so I'm not going to put that in the presentation, but if anyone is interested to find out more, I can send you the link to that. So this is the problem that we're dealing with, and we obviously do the assessments to try and prevent this happening. So how we manage half joint structures. Highways England developed and published this interim advice note 5304, which is sets out a management strategy for these half joint structures, and that's the summary there. It's quite detailed, so I'm not going to make you read it all. I've outlined the key steps here for you. So firstly, you identify your structures, how many are there, what types are they and where are they. You then go and do a visual inspection of your structures, so you see what kind of condition are they in, what defects are there. Assuming there are defects, you then go on and do some concrete testing and sampling to try and get some data, which then feeds into your fourth step, which is your structural assessment, and that's the stage that I've been working on. Based on the outcomes of the structural assessment, you then manage the risks appropriately. So that might be periodic monitoring through general inspections and principal inspections. It might be carrying out some further testing to get more data, or it could be a strengthening scheme or indeed a whole bridge replacement scheme. So just in the context of what I've been working on the area of 13 half joint assessments. So that's this red area up here in the northwest of the country. It includes Cumbria and North Lancashire, and I'm going to focus on this junction. It's junction 36 of the M6, and you can see the roundabout there. It's made up of two bridges, and these are Farleton Interchange North and South bridges. This is an extract from the as-built. They're identical structures, so you can see they're a 4-span structure. Your 2 spans at the sides, the approach spans, are made up of reinforced concrete slabs, and then your 2 central spans are made up of these precast beams which are dropped into place on site. So this structure gives us 3 types of half joints to assess. In these 2 red areas here, we have the first 2. We have the upper section of the half joint, which is made from the precast beam, and the lower section, which is made from the reinforced concrete slab which cantilever over the piers. In the centre of the bridge we have this reinforced concrete crossbeam which sits on top of the central piers, and that makes up the 3rd type of half joint, which is a lower half joint as well. So how do we actually assess these half joints? Firstly, we use what's called a strut and tie analysis. So strut and tie, it uses a truss analogy. So that means that you assume that the load is resisted through a network of compressive struts, which is made of the concrete area, and tensile ties, which is the reinforcement. According to BD 44, which is the assessment standard, you find the strut and tie capacity by adding together the capacity of 2 models, which is the inclined and the orthogonal model, and that's shown in figure B and C there. So how do we actually get the capacity from this? We look at each of the different strut or tie elements. We try and match it to the reinforcement on our particular bridge to make the arrangement work, and we then calculate the capacity of each of these elements. So for the steel, that's the yield strength and the area, and for the concrete, it's the compressive strength, the allowable stress and the available area as well. So then we start to apply a reaction to the bearing on the half joint, and the loads start to distribute through the system, so we start to stress our elements. We continue doing that, increasing the load until we get failure of the first element. So you can see here the ratio 0.999, so that element is now failing. So when you get your first failure, the corresponding reaction you're putting on your bearing, that's your capacity for that section. So you then do that for your inclined model and your orthogonal model and add them together to get your final capacity. Some issues that we've had along the way. So I've said you've got your 2 models, inclined and orthogonal. You have to be careful that you don't include the same reinforcement in both models, because this will be double counting and you'll overestimate the capacity of your half joint. For the upper half joint, you can see these blue lines. They use different reinforcements in each of the models, so we're all good there. However, for the lower half joint, this upper horizontal reinforcement is used in both models, so we've got a bit of a problem there. To overcome this problem, we essentially looked at what the available area was and we split it between the 2 models. One of the characteristics of strut and tie is that you can assess a number of different arrangements, and as long as you find one that is capable of carrying the load you want, then the whole half joint passes the assessment. So with this in mind, we were looking at the 2 systems, and we noticed that the inclined model contributes a lot more proportionally to the overall capacity than the orthogonal. So when we were splitting down the area, we didn't split 50-50, we assigned a lot more to the inclined model in order to maximise our capacity that we were getting from the strut and tie analysis. Another problem we had was applying this inclined model to the 3rd half joint, the crossbeam. If I just spin that round so it's a lower half joint and compare it to the crossbeam, so there's a compatibility issue here. For the inclined model, it assumes that there's a continuous strip of concrete beyond the half joint. However, for the crossbeam, we've got a finite concrete area. So to overcome this, we had to go back to first principles and look at how a strut and tie model is built up, what's the engineering principles behind them, and then we built up a new inclined model that was applicable to the crossbeam. So bringing this back to my example, back in context, we assessed the bridge, so we looked at the maximum applied load and compared that to our strut and tie capacities, and you can see we've got some red on the crossbeam column there, so we had some failures for a couple of load cases. So our options now, we could have suggested a strengthening scheme to bring up the condition of the bridge and increase the capacity. We could have implemented a weight restriction onto the bridge so that only this permitted traffic was allowed over the bridge, but this is obviously not a very good long-term solution. Or the third option, the one we took, was to do a second stage of assessment, which is a bit more refined, try and calculate a more accurate capacity, which is hopefully a bit higher and will allow us to pass. So that brings me on to the collapse mechanism analysis, which was our second type of assessment. This works by, you assume a failure crack, which is shown by the red line, and you then assume that the half joint fails by the top section rotating around the top of that crack, which is point O. In order to do this, you consider the free body diagram to the left hand side of the crack, and you take moment equilibrium about that point O, so you equate the internal and the external energies to work out your capacity. So the internal energy, you assume that any reinforcement bars that are crossing the crack yield in tension, and you assume that that area of concrete above the top of the crack is crushing in compression, it's at its yield strength. And then you balance that with your external energy, which is formed from your applied loading, and you times it by the lever arm to point O to work out your moment. So contrary to strut and tie, for collapse mechanism you need to try a range of different solutions, different arrangements, different shapes of crack, and if any one of these fails the assessment, then the whole structure fails. So we had to test a real large number of crack formations, and we had to put that point O in various different locations to try and find the minimum capacity. Some issues that we had with collapse mechanism, as I've just said, we had to do a range of iterations, is where do we put that point O? There could be infinite options. So in the X direction, you'll notice we've got some quite nicely spaced vertical links which cover the whole range of the half joints. So that was nice and convenient to consider point O at each of those links in turn. For the vertical height for YO, it's slightly less well defined. So what we did, we considered again our free body to the left hand side of the track, and we did a horizontal force equilibrium. So essentially what we did, we worked out what depth of concrete in compression do we need to resist the forces from the steel and to have equilibrium in that section. So we did that to work out the depth of concrete we needed and then the corresponding height of YO. Another problem we've got, you can see the bar highlighted here, it ends in the region of the half joint, so you've got potential problems with anchorage of this bar. So that means that where we've initially assumed that the bar is going to yield in tension, it could prematurely fail by anchorage failure before it reaches that yield point. So to overcome this, I looked at the geometry in the region of the anchorage length and derived some quite simple geometric equations to put into the spreadsheet, so it could then calculate for us for each iteration if the bar is going to fail by yielding or by anchorage. We do have a slight problem here. You'll notice in the anchorage length equation we have this point YO. So we need to know that to work out the anchorage length. Unfortunately, to work out the height of YO, we also need to know the anchorage length to know the horizontal forces in the bars. So we have a circular reference here. To overcome this, we looked at that horizontal force equilibrium equation and used the goal-seek function in Excel to work out that depth of concrete required to balance out the section and make it all work. Goal-seek, if anyone's used it, it's a manual calculation in Excel. It's very time consuming where we've got dozens of iterations. So what we did, we developed a macro in Excel, and you can simply push a button and it'll perform hundreds of these calculations in a matter of seconds. So bringing me back to Farlington Interchange, using the strut and tie and the collapse mechanism assessments, we've got the structure to pass for all load cases. So that's great news for us. it brings me out to the outcomes and the benefits of the project. So the biggest outcome was that we've been successful in delivering our services to our client in Highways England, helping them to manage these real large-scale, high-risk structures, so making sure that they're fit for purpose, they're adequate to carry their load, and there's no risk to the network users. I mentioned before, one of our options after the strut and tie was to do a strengthening scheme. Had we not done our second stage assessment and got the structure to pass, if we'd have done a strengthening scheme, strengthening schemes on half joints, as I mentioned, they're very inaccessible structures, so it's difficult to go and do maintenance works. So your only real options are to sort of jack the whole bridge deck up, do your strengthening works and then lower it back down, or alternatively you do a whole bridge deck replacement. So these schemes, they're not minor schemes, it's very cost intensive, very labour intensive, and it uses a lot of materials. So by doing our second stage assessment and getting it to pass, we've got a much more sustainable solution, both economically and environmentally, and we've also prevented a lot of construction workers from going out to site on these main roads and putting themselves in a lot of harm's way. So that's another win. Half joint assessment methodology, it's not a well-trodden path. As we've been going along, we've been shaping it, we've been ironing out these issues, so we've really been enhancing the current body of knowledge. So that's obviously beneficial to the company, to the client, and to the industry as a whole. In addition to that, personally, I've developed a lot working on this scheme, both technically and in terms of project management. It's a real large scheme. I've really championed continuous improvement on this scheme. I've initiated and encouraged the use of a lessons learnt register. So as we've gone along, any issues we encounter, any disagreements we have, the outcomes of those we document in an easily referenced place, which we can then circulate to future half-joint assessment teams and prevent repeat mistakes from occurring. Also, in terms of continuous improvement, this is what led me to write my paper, which is why I'm here today. So this paper outlines all of the learning that we've done over the past year and brings together in one comprehensive document all of the assessment methodologies. So it enables future assessments to be done more accurately and efficiently, and it also promotes consistency, so they're all done the same way within the same programme. So the idea is a new engineer who's working on a half-joint assessment can pick up this guide, have a read through, and they'll have a comprehensive sort of base knowledge of how they do the assessment. Just one final note, I mentioned that half-joint methodologies are sort of, they're developing, it's not a final thing. So this document is intended as a live document to be added to and to be amended as we go along. So hopefully as we get further and further down the line and refine the method, its usefulness and effectiveness will increase. So thank you for listening. I hope I've given you a brief overview of the assessment methodology for half joints. I hope you found it interesting, not too confusing. So thank you, and I welcome any questions that you have.